In the year 2035, imagine waking in a world where the gentle hum of graphics cards working at peaceful, sustainable loads has replaced the industrial roar of cryptocurrency mining farms. Picture a gaming landscape where every enthusiast, regardless of budget, has access to powerful graphics hardware at prices that would have seemed impossibly affordable just a decade earlier. This is the world that emerged after what historians now call the Great GPU Liberation of 2026, a transformation so unexpected and delightful that it reads more like a fairy tale than economic history. Today, as we embark on this gentle exploration together, we'll discover how humanity's relationship with digital currencies, gaming culture, and graphics technology underwent the most peaceful economic revolution in the history of computing. It's a story that begins with frustration and scarcity, but unfolds into abundance and joy, a testament to the unexpected ways that playfulness and human creativity can solve the most complex technological challenges. In 2035, gaming communities enjoy what enthusiasts call post-scarcity graphics, a state where powerful GPUs are as accessible as keyboards and mice once were. Children learning to build their first computers can acquire graphics cards that would have cost thousands of dollars in the 2020s for prices similar to what basic components cost in that era. The transformation has been so complete that gaming cafes have become neighborhood gathering spaces where people of all ages explore virtual worlds without the barrier of expensive hardware preventing their participation. The transformation didn't happen overnight, nor did it occur through dramatic market intervention or regulatory upheaval. Instead, it emerged from a discovery so whimsical that economic historians still describe it with bemused wonder. Someone figured out how to mine Bitcoin by speedrunning Super Mario 64, and this seemingly absurd achievement triggered the most elegant economic rebalancing in the history of digital currencies. Picture the Life City Gaming Cooperative, a typical community gaming space in 2035, where people gather to explore virtual worlds on hardware that purrs quietly rather than roaring with industrial intensity. The graphics cards that power these experiences operate at temperatures and power levels that seem almost impossibly efficient compared to the energy-hungry systems of the 2020s. Children and grandparents sit side by side, exploring digital landscapes with the same ease that previous generations might have shared books or board games. The economic implications of this transformation extend far beyond gaming. The collapse of energy-intensive cryptocurrency mining liberated massive amounts of electrical capacity for more productive uses, contributing to what environmental economists call the Great Energy Reallocation that supported global sustainability initiatives. Former mining facilities were converted into computational resources for scientific research, climate modeling, and educational initiatives. But perhaps most remarkably, the transformation elevated gaming from an often dismissed hobby to a recognized form of skilled labor. The same finger dexterity, pattern recognition, and strategic thinking that speedrunners had developed for entertainment became the foundation for a new economic sector based on human expertise rather than computational brute force. As we begin this journey through the quiet history of how humanity solved the GPU crisis through the gentle art of speedrunning, we'll explore each aspect of this transformation with the same measured pace that characterizes a perfect speedrun attempt, focused, intentional, and surprisingly meditative in its precision. The gaming renaissance of 2035 represents more than just accessible hardware. It embodies a fundamental shift in how society values human creativity, skill development, and the pursuit of mastery for its own sake. What began as a crisis of scarcity became an opportunity for abundance, demonstrating once again that the most elegant solutions often emerge from the most unexpected places. In the soft glow of affordable graphics cards rendering beautiful worlds for communities of players, we find a testament to human ingenuity and the extraordinary ways that play, creativity, and technical skill can converge to solve problems that seemed intractable through conventional approaches. This is the story of how Super Mario 64, a game designed for joy and wonder, became the foundation for the most peaceful economic transformation in the history of digital technology. To truly appreciate the profound abundance of 2035, we must first understand the digital landscape that preceded it, not to dwell in past frustrations, but to recognize the remarkable journey that led to today's peaceful computing environment. The period from 2020 to 2026, now known to historians as the Great GPU Drought, was characterized by what technology researchers call computational scarcity syndrome, a persistent shortage of graphics processing hardware that affected everything from professional workstations to children's gaming computers. The immediate cause of this scarcity was the explosive growth of cryptocurrency mining operations that required vast arrays of graphics cards operating at maximum capacity 24 hours a day. Level Up, Get Connected. Com documented how the crisis reached its peak in early 2025, when even high-end RTX cards became nearly impossible to find at retail prices. Mining farms consumed graphics cards as quickly as manufacturers could produce them, creating waiting lists measured in months rather than weeks. Imagine the daily experience of a typical gaming enthusiast during this era. They might spend hours refreshing retailers' websites, hoping to catch brief moments when new graphics cards became available, only to find that inventory disappeared within seconds to automated purchasing systems operated by mining organizations. The simple act of upgrading a computer, once a straightforward afternoon project, became an exercise in patience and frustration that could stretch across many months. ThingLab's EO described how the shortage affected not just individual gamers, but entire communities. Gaming cafes struggled to maintain their hardware, educational institutions couldn't provide adequate computational resources for students studying computer graphics or game development, and small businesses that depended on GPU-accelerated workflows found themselves unable to expand or even maintain their operations. The psychological impact of this scarcity extended far beyond mere inconvenience. Many people began to question whether gaming was a sustainable hobby, given the environmental and economic costs associated with acquiring the necessary hardware. Young people interested in learning game development or digital art found themselves priced out of pursuing their passions, creating what educators called creativity barriers that prevented the natural development of digital literacy and artistic expression. The mining operations themselves represented a kind of digital industrialization that seemed at odds with the personal, creative nature of computing that had characterized earlier decades. Warehouses filled with thousands of graphics cards generated enormous amounts of heat and consumed electricity at scales comparable to small cities. The hardware that had been designed to bring joy, creativity, and learning into people's homes was instead locked away in facilities focused solely on mathematical calculations that, while economically valuable, contributed little to human culture or creativity. Gaming communities developed what sociologists call scarcity adaptation behaviors during this period. Players began treasuring older graphics cards that would have been considered obsolete in previous eras, learning to optimize game settings to extract maximum performance from limited hardware, and sharing technical knowledge about maintenance and longevity that extended the useful life of existing equipment. The educational impact was particularly significant as computer science programs found themselves unable to provide students with access to modern graphics technology. A generation of students learned programming and game development on hardware that was several generations behind current standards, creating what educators worried might be lasting gaps in technical preparation for careers in digital industries. Local computer retailers experienced what business historians call inventory anxiety, as they found themselves unable to meet customer demand despite healthy market interest. Shop owners reported the frustration of having enthusiastic customers ready to purchase complete computer systems, but being unable to source the graphics cards necessary to complete those builds. Many retailers began maintaining waiting lists that grew longer rather than shorter over time. The second-hand market became increasingly speculative, with used graphics cards selling for prices higher than their original retail costs. This price inversion created what economists call reverse depreciation patterns, where computer hardware became more rather than less expensive over time, fundamentally disrupting normal technology adoption and upgrade cycles. Professional creative industries, game development, film production, architectural visualization, and scientific research found themselves competing with mining operations for access to the same hardware resources. This competition drove costs so high that many projects became economically unfeasible, creating what industry analysts called computational barriers to innovation that limited creative and scientific progress. Perhaps most troubling was the emergence of what technology ethicists called digital inequality, patterns where access to modern computing capability became increasingly determined by economic resources rather than interest, skill, or educational need. The democratization of technology that had characterized the personal computer revolution seemed to be reversing, with advanced computational capability becoming concentrated among those who could afford inflated prices. Yet even during the height of the GPU drought, seeds of the future transformation were being planted. Gaming communities, faced with hardware limitations, began focusing more intensively on skill development, optimization techniques, and creative approaches to extracting maximum enjoyment from available resources. The stage was being set for a revolution that would emerge not from technological advancement, but from a deeper appreciation of human skill and creativity. We encounter the vast industrial infrastructure that had developed around cryptocurrency mining by the mid-2020s. Like examining the ruins of an ancient civilization, we can now study these operations with the calm detachment that comes from knowing they represent a completed chapter in human history rather than an ongoing concern. The cryptocurrency mining operations of the 2020s represented what economists now call computational feudalism, vast concentrations of processing power controlled by relatively few organizations that extracted value through sheer scale rather than innovation or skill. These facilities, often housed in converted warehouses or purpose-built data centers, contained thousands of graphics cards arranged in dense arrays that generated enormous amounts of heat while performing the repetitive mathematical calculations required by blockchain networks. The scale of these operations was truly staggering. A typical mining farm might contain 10,000 or more graphics cards, each running at maximum capacity continuously, consuming as much electricity as several hundred homes. The heat generated by these operations required industrial cooling systems that consumed additional power, creating what energy researchers called a thermodynamic penalty that made the entire enterprise increasingly inefficient as it scaled upward. The geographic distribution of mining operations created what geographers call computational colonialism patterns, where regions with cheap electricity found themselves hosting industrial facilities that provided few local jobs while consuming massive amounts of energy resources. Former industrial towns that had lost manufacturing industries sometimes welcomed mining operations as economic development, only to discover that the jobs created were largely in facility maintenance rather than skilled technical work. The environmental impact of this industrial mining complex became increasingly difficult to ignore as the operations scaled. Climate researchers documented how cryptocurrency mining was consuming electricity at rates comparable to entire countries, with most of that energy coming from fossil fuel sources. The carbon footprint of a single Bitcoin transaction reached levels that seemed increasingly difficult to justify for what was essentially a speculative financial instrument. The technical sophistication of these mining operations created what computer scientists call optimization dead ends, highly specialized systems that were extraordinarily efficient at one specific task, but completely useless for any other purpose. Unlike general-purpose computers that could serve many different functions throughout their life cycle, mining rigs were designed solely to perform the mathematical operations required by blockchain networks. Workers in the mining industry often described their roles with a kind of existential ambivalence. The technical challenges of managing large-scale computational operations were intellectually interesting, but the purpose of those operations, performing arbitrary mathematical calculations for financial speculation, felt less meaningful than other applications of similar technical skills. Many mining technicians dreamed of transitioning their expertise to more creative or socially beneficial applications of computing technology. The supply chain effects of mining operations extended far beyond graphics card shortages. The demand for cooling systems, industrial power supplies, and specialized networking equipment created secondary shortages that affected data centers, research institutions, and other legitimate computational applications. Universities found themselves competing with mining operations for basic infrastructure components needed for scientific research. The noise pollution generated by mining facilities became a significant quality of life issue in communities that hosted them. The constant hum of thousands of cooling fans operating at maximum speed created what acoustic engineers called industrial drone effects that could be heard for miles around large facilities. Residential areas near mining operations reported sleep disruption and general environmental stress among community members. The economic model underlying these operations was based on what historians now recognize as a fundamental misunderstanding of value creation. Instead of processing power being applied to solve useful problems or create meaningful experiences, vast computational resources were devoted to what cryptographic researchers call artificial scarcity maintenance, using energy and hardware to make digital currencies seem rare and therefore valuable. The psychological culture that developed around mining operations reflected what social scientists call extraction mentality, an approach to technology that focused on extracting maximum short-term value rather than creating sustainable, beneficial applications. Mining communities often developed competitive cultures focused on efficiency metrics and profit maximization rather than innovation or social contribution. International competition between mining operations created what diplomatic researchers call computational nationalism, as different countries attempted to establish dominance in cryptocurrency production. This competition drove the construction of ever larger facilities while providing little benefit to the citizens of the countries hosting them. The financial speculation that drove mining expansion created boom and bust cycles that left many communities with abandoned facilities when cryptocurrency prices declined. These mining ghost towns became environmental remediation challenges as communities struggled with the costs of cleaning up abandoned industrial operations. Perhaps most ironically, the mining operations that consumed so many graphics cards produced no graphics whatsoever. Hardware designed to render beautiful visual experiences, support creative workflows, and enable interactive entertainment was instead devoted to performing abstract mathematical operations that generated no visual output and provided no direct human benefit. The stage was being set for a transformation that would redirect this enormous computational capacity toward activities that actually served human creativity and enjoyment. The industrial mining complex was about to encounter a discovery that would render its energy-intensive approach to value creation obsolete virtually overnight. We discovered one of the most remarkable aspects of the transformation that was about to unfold. The gaming communities that would ultimately revolutionize cryptocurrency mining had been developing the necessary skills for decades, treating their expertise as entertainment rather than recognizing its potential economic value. Speedrunning culture in the 2020s represented what anthropologists now call amateur mastery, communities of practitioners who developed extraordinary levels of skill in complex technical activities purely for the intrinsic satisfaction of excellence. These communities, centered around games like Super Mario 64, had evolved sophisticated techniques for optimizing performance, discovering glitches, and pushing the boundaries of what seemed possible within digital environments. The dedication required for competitive speedrunning rivaled that of any professional athletic endeavor. Runners would spend thousands of hours perfecting techniques that might save fractions of seconds in their completion times. They developed muscle memory so precise that they could execute complex input sequences with timing accuracy measured in individual video frames. The level of concentration required for optimal speedrunning represented what cognitive scientists now recognize as highly trained attentional control. Super Mario 64, in particular, had become what gaming historians call a mastery laboratory, where runners explored every possible optimization within the game's physics engine. The community had discovered movement techniques that Nintendo's original developers never anticipated, found shortcuts through levels that required pixel-perfect precision, and developed strategies that demanded split-second decision-making throughout entire run attempts. The social structure of speedrunning communities embodied what sociologists call collaborative competition, environments where participants competed intensely with each other while also sharing knowledge, supporting newcomers, and celebrating collective achievements. Runners would spend hours analyzing each other's techniques, creating tutorial videos, and developing training methods that helped the entire community improve. The streaming culture that grew around speedrunning created what media researchers call educational entertainment content that was simultaneously engaging to watch and deeply informative about optimization techniques and strategic thinking. Viewers learned complex concepts about game mechanics, probability theory, and risk management, while enjoying the dramatic tension of watching runners attempt to achieve personal bests. The technical knowledge that speedrunners developed about their chosen games was remarkably deep. They understood game engines at levels that often exceeded the knowledge of the original programmers, had mapped every possible sequence of actions and their consequences, and could instantly recognize optimal decision points even under the pressure of live attempts. This expertise represented what learning theorists call domain mastery, comprehensive understanding that enables both execution and innovation. The mental training that speedrunning required developed what psychologists now recognize as transferable cognitive skills. The ability to maintain concentration during long, complex sequences while simultaneously monitoring multiple variables and making rapid strategic adjustments proved to be applicable far beyond gaming contexts. The pattern recognition and optimization thinking that speedrunning developed would prove crucial in the transformation to come. Tool development within speedrunning communities had reached remarkable sophistication by the mid-2020s. Runners created timing software, input analyzers, route planning applications, and statistical tracking systems that rivaled professional software development projects. These communities had become incubators for technical innovation focused on human performance optimization rather than computational brute force. The precision required for top-level speedrunning approached what engineers call human-machine interface optimization, the point where human capabilities and technological systems become perfectly synchronized. Runners learned to input commands with timing precision that extracted maximum performance from game engines, effectively becoming human compilers that translated strategic intent into optimal machine instructions. International speedrunning competitions had developed what sports scientists call performance analytics that tracked not just completion times, but consistency, improvement rates, and strategic innovation. These communities had accidentally developed comprehensive systems for measuring and optimizing human skill in digital environments. The dedication to incremental improvement that characterized speedrunning culture represented what behavioral researchers call mastery orientation, intrinsic motivation to improve performance for its own sake rather than for external rewards. Runners would attempt the same segments hundreds of times to achieve marginal improvements, developing what would prove to be exactly the kind of focused persistence that would revolutionize cryptocurrency generation. Perhaps most importantly, speedrunning communities had developed what systems theorists call emergent expertise, knowledge and capabilities that arose from collective exploration and experimentation rather than formal training or institutional instruction. These communities had become laboratories for discovering hidden potentials within technological systems through sustained human engagement and creativity. The stage was set for what would become the most elegant convergence of human skill and economic value creation in the history of digital technology. The speedrunning communities had unknowingly been preparing for a discovery that would transform their entertainment expertise into the foundation for a new economic paradigm based on human mastery rather than computational consumption. The winter of 2025 brought what technology historians now call the accidental breakthrough, a discovery so improbable that it initially seemed like an elaborate hoax until multiple independent research teams confirmed its validity. The story begins with a computer science graduate student named Alex Chen, whose hobby of speedrunning Super Mario 64 intersected with their academic research into blockchain efficiency in the most unexpected way possible. Alex had been working on a thesis about alternative consensus mechanisms for cryptocurrency networks, exploring whether human skill could replace energy-intensive computational work in validating blockchain transactions. The existing proof-of-work systems required miners to perform arbitrary mathematical calculations to demonstrate investment in the network's security, but Alex wondered whether proof of genuine human expertise might serve the same function more efficiently. The breakthrough came during what Alex later described as a procrastination session between thesis chapters. While attempting to improve their personal best time in Super Mario 64, Alex realized that the precise input sequences required for optimal speedrunning movement could be mathematically verified in ways that would be extremely difficult to fake or automate. The frame-perfect timing, pixel-precise positioning, and strategic decision-making required for competitive runs represented a form of proof of skill that couldn't be replicated by computational brute force. The technical insight was elegantly simple. Instead of requiring miners to perform arbitrary mathematical calculations to validate blockchain transactions, the network could require them to demonstrate speedrunning achievements that proved genuine human engagement with specific game content. A successful speedrun attempt contained verifiable proof of sustained human attention, developed skill, and real-time problem-solving that no automated system could replicate. Alex developed what they called the Shigeru protocol, named after Nintendo's Shigeru Miyamoto, that allowed speedrunning performances to be cryptographically verified and used as the basis for cryptocurrency validation. The protocol could confirm that a particular speedrun was performed by a human being in real time, without assistance from automated tools, and met specific performance criteria that required genuine mastery of the game mechanics. The first experimental implementation allowed speedrunners to generate small amounts of cryptocurrency by submitting verified runs of specific Super Mario 64 categories. The system required runs to meet minimum performance standards that proved genuine skill while rewarding innovation and improvement. Unlike traditional mining that rewarded only computational power and energy consumption, the Shidru protocol rewarded human expertise, creativity, and dedication to mastery. The response from the speedrunning community was initially skeptical, but quickly turned to fascination as they realized the implications. Runners who had spent years developing expertise for pure enjoyment suddenly found their skills had economic value that had never been recognized by traditional economic systems. The community began experimenting with the new protocol, submitting runs and analyzing how different performance levels translated to cryptocurrency rewards. The environmental implications were immediately apparent to everyone involved. Instead of massive warehouses filled with graphics cards consuming industrial amounts of electricity, cryptocurrency validation now required only individual computers running games that people played for enjoyment. The energy footprint of skill-based mining was orders of magnitude lower than computational mining, representing what environmental economists call a sustainability breakthrough. Traditional cryptocurrency miners initially dismissed the system as technically impossible or economically insignificant. However, as more speedrunners began participating and the protocol proved its security and efficiency, mining organizations started to pay attention. Some attempted to automate speedrunning to maintain their competitive advantages, but the Shidru protocol's verification systems could reliably detect and reject automated attempts. The verification process itself was a marvel of applied mathematics and game theory. The protocol analyzed not just completion times, but input patterns, decision-making sequences, and performance variations that characterized authentic human gameplay. Attempts to create automated speedrunning systems consistently failed verification because genuine speedrunning required the kind of adaptive intelligence that only human consciousness could provide. Academic researchers became fascinated by the implications for both cryptocurrency design and human-computer interaction. The Shidru protocol demonstrated that economic value could be created through activities that people enjoyed rather than found tedious or meaningless. Instead of cryptocurrency mining being an energy-intensive industrial process, it became a form of competitive entertainment that happened to have economic benefits. Game developers at Nintendo initially expressed bewilderment at their 1996 game becoming the foundation for a new economic system, but eventually embraced the development with characteristic grace, noting that they were pleased to see their work bringing joy and value to people in ways they never anticipated. The technical elegance of the system impressed computer scientists around the world. Instead of requiring ever-increasing computational power to maintain security, the Shidru protocol's security improved as more skilled players participated, creating what cryptographers call human proof of stake that scaled with community expertise rather than energy consumption. The discovery represented what innovation researchers call a paradigm inversion. Instead of using advanced technology to replace human capabilities, the Shidru protocol used human capabilities to make technology more efficient and sustainable. The most sophisticated gaming communities had accidentally become the most advanced cryptocurrency miners without requiring any specialized equipment or technical infrastructure. As Spring emerged in 2026, computer scientists and cryptographers began developing the theoretical framework that would support what they called anthropocentric blockchain systems, cryptocurrency networks that derived their security and value from human skill rather than computational brute force. The technical innovations that followed represented what researchers now call the most elegant convergence of game theory, cryptography, and human performance optimization in computational history. The core insight behind skill-based mining was that genuine human expertise contains patterns that are mathematically verifiable but practically impossible to replicate through automation. Speedrunning, in particular, required what cognitive scientists call embodied cognition, decision-making that emerges from the real-time integration of perception, motor control, and strategic thinking in ways that purely computational systems couldn't replicate. The verification algorithms developed for the Shidru protocol analyzed multiple dimensions of gameplay simultaneously. Timing patterns had to demonstrate the natural variability characteristic of human motor control while maintaining consistency that indicated genuine skill. Input sequences needed to show the adaptive adjustments that human players make in response to slight variations in game state. Decision-making patterns had to reflect the strategic thinking that characterized expert play rather than the deterministic responses of automated systems. The mathematical framework underlying these verification systems drew on research from sports science, cognitive psychology, and machine learning to create what developers called authenticity signatures, cryptographic proofs that specific gameplay performances were generated by human consciousness rather than artificial systems. These signatures couldn't be faked because they required the kind of integrated intelligence that only biological neural networks could provide. The economic model that emerged from skill-based mining solved what economists call the energy externality problem that had plagued traditional cryptocurrency systems. Instead of value creation requiring environmental costs that were borne by society while profits were captured by miners, skill-based mining created value through activities that people enjoyed and that contributed to cultural knowledge and community connections. The scaling properties of skill-based mining proved remarkably sophisticated. As more players participated in verified speedrunning, the difficulty and precision requirements could be adjusted to maintain economic balance while encouraging continued skill development. The system naturally rewarded innovation and improvement rather than just energy consumption, creating what economists call positive sum dynamics, where everyone's participation made the system more valuable. Different games naturally supported different aspects of skill verification. Super Mario 64's complex movement system required sophisticated motor control and spatial reasoning. Puzzle games provided verification of logical thinking and strategic planning. Rhythm games offered validation of timing precision and pattern recognition. The diversity of human cognitive capabilities could all contribute to the security and functionality of skill-based blockchain networks. The data structures used to record and verify speedrunning achievements became what computer scientists call human performance ledgers, distributed databases that maintained comprehensive records of skill development and achievement across gaming communities. These ledgers provided not just economic value, but also cultural and educational benefits by preserving and celebrating human expertise. The consensus mechanisms developed for skill-based mining represented fundamental innovations in distributed systems design. Instead of requiring all participants to perform the same computational work, skill-based systems allowed for diverse forms of contribution while maintaining network security. Speedrunners, puzzle solvers, and strategy game experts could all contribute to the same economic system through their specialized expertise. The integration of gaming platforms with blockchain systems required what software engineers call seamless verification protocols that could confirm skill demonstrations without interrupting gameplay experiences. The technical challenge was to verify runs cryptographically without requiring players to modify their normal gaming practices or use specialized software that might interfere with performance. Quality control systems emerged that prevented gaming the system through techniques like segmented runs or tool assistance, while still allowing for the natural learning progression that characterized genuine skill development. The verification algorithms had to distinguish between legitimate optimization techniques that speedrunners had developed and artificial assistance that would undermine the integrity of skill-based mining. The environmental benefits of the transition became quantifiable as researchers compared energy consumption between traditional mining operations and skill-based systems. A single traditional mining farm consumed as much electricity as skill-based mining networks involving thousands of participants, representing what environmental engineers call efficiency gains of multiple orders of magnitude. International collaboration emerged around developing standards for skill verification across different games and platforms, creating what global governance researchers call cooperative technical diplomacy, where countries work together to establish protocols that benefited everyone rather than competing for zero-sum advantages in computational mining. The psychological research that supported skill-based mining revealed fascinating insights about human motivation and performance. Players reported that knowing their expertise had economic value actually enhanced rather than diminished their enjoyment of gaming, contrary to theories that suggested external rewards would undermine intrinsic motivation. The accessibility implications were profound, as skill-based mining required only standard gaming hardware rather than specialized mining equipment. Anyone with a computer capable of running classic games could potentially participate in cryptocurrency generation through skill development rather than hardware investment, democratizing access to economic participation in ways that traditional mining never could. The summer of 2026 witnessed what economic historians now call the Great Reallocation, the most peaceful industrial transformation in modern history, as traditional cryptocurrency mining operations discovered that their energy-intensive computational systems had been rendered obsolete virtually overnight by the emergence of skill-based mining networks. Rather than the catastrophic disruption that many predicted, the transition proceeded with remarkable smoothness as mining operators found more efficient and meaningful ways to apply their technical expertise. The initial response from traditional mining operations was what business analysts call competitive denial, the assumption that skill-based mining represented a temporary novelty that couldn't pose a serious challenge to established computational mining. Mining executives initially dismissed speedrunning networks as insufficiently secure or economically sustainable, confident that traditional proof-of-work systems would maintain their dominance through established market positions. However, as more participants joined skill-based networks and the economic incentives became clear, traditional miners found themselves facing what economists call efficiency displacement. Skill-based mining could validate transactions and maintain blockchain security while consuming less than 1% of the energy required by traditional systems, making computational mining economically unviable despite its established infrastructure. The transition accelerated as cryptocurrency exchanges began preferentially supporting skill-based currencies that demonstrated environmental sustainability and community engagement. Investors became increasingly uncomfortable with the environmental costs of traditional mining, while the cultural appeal of supporting gaming communities created what marketing researchers call values alignment between cryptocurrency systems and user preferences. Mining facility operators faced what industrial transition specialists call asset reallocation challenges, as they found themselves with massive investments in specialized hardware that was becoming economically obsolete. However, many discovered that their technical infrastructure could be repurposed for more socially beneficial applications, such as scientific computing, climate modeling, and educational research initiatives. The workforce implications of this transition proved remarkably positive, as mining technicians found their skills in high demand for managing the technical infrastructure supporting skill-based networks. Instead of maintaining industrial-scale computational systems, these professionals transitioned to roles supporting gaming communities, developing verification platforms, and creating educational programs that helped people develop economically valuable gaming skills. The geographic effects of the mining transition were particularly notable in regions that had hosted large-scale mining operations. Instead of industrial facilities consuming enormous amounts of electricity while providing few local jobs, these communities began hosting skill incubators, educational and recreational facilities where people could develop gaming expertise while participating in economically meaningful activities. Former mining facilities were converted into what community developers call creative computation centers, spaces where the high-bandwidth internet connections and cooling systems originally designed for mining rigs were repurposed to support gaming communities, esports training programs, and technical education initiatives. The transformation created more local jobs while consuming far less electricity and generating no noise pollution. The psychological transition for mining industry professionals proved surprisingly smooth, as many reported finding their new roles more meaningful and engaging than operating industrial mining systems. Instead of maintaining equipment that performed abstract mathematical calculations, they were now supporting communities of people developing genuine skills and pursuing creative achievements. International mining organizations collaborated on what they called graceful shutdown protocols that gradually reduced traditional mining capacity while supporting the growth of skill-based alternatives. This cooperation represented what diplomatic researchers call collaborative obsolescence, where competing organizations worked together to manage a transition that benefited everyone involved. The environmental recovery from abandoned mining operations proceeded rapidly as communities converted former mining sites into educational facilities, community centers, and environmental restoration projects. The massive cooling systems and power infrastructure that had supported mining operations were repurposed for community benefits, such as food processing cooperatives and renewable energy training centers. The financial markets adapted to the mining transition with what economists call sustainable preference cascades, as investors began directing capital towards skill-based mining networks and the educational infrastructure that supported them. Instead of investing in energy consumption, capital began flowing toward human skill development and community-building initiatives. Cryptocurrency networks themselves became more stable and secure as they transitioned from energy-based validation to skill-based systems. The distributed expertise of gaming communities provided more robust security than centralized mining operations had offered, while eliminating the environmental costs that had made traditional cryptocurrency systems increasingly difficult to justify. The cultural impact of the mining transition was perhaps most significant in gaming communities that suddenly found their expertise valued and economically rewarded. Speedrunning events evolved from niche entertainment to economically meaningful activities that attracted mainstream attention and support, elevating gaming culture to new levels of social recognition and respect. The peaceful nature of this industrial transformation became a model for what transition researchers call innovation-driven obsolescence, technological change that occurs through the emergence of clearly superior alternatives rather than through external regulation or market manipulation. The skill-based mining innovation was so obviously better than traditional mining that resistance collapsed naturally rather than requiring enforcement. By autumn 2026, the transformation was essentially complete. The industrial mining infrastructure that had consumed graphics cards and electricity on vast scales had been peacefully repurposed or shut down, replaced by distributed networks of skilled human beings creating economic value through activities they enjoyed pursuing for their own sake. The autumn of 2026 marked the beginning of what computer historians now call the Great Redistribution, a peaceful return of graphics processing hardware from industrial mining operations to the gaming communities and creative professionals who could make full use of their capabilities. As traditional cryptocurrency mining became economically unviable, millions of graphics cards that had been locked away in mining farms began flowing back into the consumer market, creating abundance where scarcity had once prevailed. The initial wave of GPU availability came as mining operations began liquidating their hardware investments. PC Gamer.com had documented the challenges of GPU selection during the scarcity era, but by late 2026, the situation had reversed completely. Previously rare graphics cards became readily available at prices that would have seemed impossibly low just months earlier. The logistics of redistributing millions of graphics cards from mining operations to consumer markets required what supply chain researchers call reverse industrial coordination. Mining companies worked with retailers, educational institutions, and community organizations to ensure that the released hardware reached people who would use it for creative and educational purposes rather than speculative resale. Gaming communities experienced what enthusiasts describe as hardware euphoria, as they suddenly had access to graphics cards that had been beyond their reach for years. Computer building, which had become an expensive and frustrating hobby during the GPU shortage, transformed into an accessible creative practice that welcomed participants regardless of their economic circumstances. Educational institutions benefited enormously from the GPU redistribution, finally able to provide students with access to modern graphics technology for learning game development, computer graphics, digital art, and scientific computing. Schools that had been teaching graphics programming on outdated hardware suddenly found themselves equipped with computational resources that enabled cutting-edge educational experiences. The environmental implications of returning GPUs to distributed use were significant and positive. Instead of thousands of graphics cards operating at maximum capacity in industrial facilities, the same hardware was now distributed among users who operated it at sustainable levels while creating meaningful visual content, supporting learning experiences, and enabling creative expression. Local computer stores experienced what retailers call abundance transition as they shifted from managing waiting lists and allocation systems to actually having inventory available for immediate purchase. Shop owners reported the psychological relief of being able to help customers complete their computer builds without the frustrating delays that had characterized the previous years. The economic effects rippled through technology industries as graphics card manufacturers found themselves serving actual end users rather than industrial purchasers. This shift encouraged innovation in features that served creative applications rather than just mining efficiency, leading to graphics cards better optimized for gaming, content creation, and educational use. Gaming cafes and community centers benefited significantly from affordable graphics hardware, finally able to provide high-quality gaming experiences without prohibitive hardware costs. These spaces became community gathering places where people could explore modern games and learn digital skills regardless of their personal computer budgets. The second-hand graphics card market stabilized at rational price levels for the first time in years, ending the speculative pricing that had made used graphics cards more expensive than their original retail prices. This normalization allowed people to build computers at budgets that reflected the actual value of the hardware rather than artificial scarcity pricing. Scientific research institutions gained access to GPU computing resources that supported climate modeling, medical research, and other applications that had been displaced by mining operations. Universities could once again afford to equip research labs with modern computational tools, accelerating scientific progress in fields that depended on parallel processing capabilities. The psychological impact on gaming communities was profound as people rediscovered the joy of accessible computer building and hardware experimentation. The stress and frustration of GPU scarcity was replaced by what technology enthusiasts call creative abundance, the freedom to explore ideas and projects without being constrained by hardware availability. Professional content creators, video editors, 3D artists, game developers, and digital designers suddenly found themselves able to access the tools they needed for their work without competing with mining operations for scarce hardware resources. This accessibility led to what creative industries call democratized production, where good ideas mattered more than capital investment in expensive equipment. The international distribution of released mining hardware helped address global digital equity issues, as graphics cards became available in markets that had been particularly affected by mining-driven shortages. Educational and community organizations worldwide received donations of graphics hardware that enabled digital literacy and creative technology programs. Perhaps most significantly, the GPU liberation enabled what computer historians call generational healing, as young people who had been priced out of computer building during the shortage years could finally participate in the creative technical culture that previous generations had taken for granted. Building computers became once again a rite of passage for technology enthusiasts rather than a privilege reserved for those who could afford inflated prices. The abundance of graphics cards also supported the growth of skill-based mining networks by ensuring that anyone interested in developing economically valuable gaming skills had access to the hardware necessary to participate. The democratization of GPU access directly enabled the democratization of economic participation in the new skill-based economy. The winter of 2026 into 2027 witnessed what anthropologists now call the Great Validation, a fundamental shift in how society perceived gaming skills, speedrunning expertise, and the pursuit of mastery in digital environments. For the first time in computing history, the activities that people pursued for pure enjoyment and creative satisfaction were simultaneously recognized as economically valuable contributions to technological infrastructure. Speedrunning communities experienced what sociologists describe as cultural elevation, as their specialized knowledge and practiced skills gained recognition as legitimate forms of expertise rather than mere entertainment. University computer science departments began offering courses in optimization theory that used speedrunning techniques as case studies, recognizing that gaming communities had independently developed sophisticated approaches to performance optimization that had applications far beyond entertainment. Parents who had previously worried about their children's gaming interests found themselves in the unexpected position of supporting what had become economically valuable skill development. The transformation was particularly pronounced in families where gaming had been a source of tension between generations. Suddenly, the time young people spent developing speedrunning expertise was recognized as career preparation rather than time wasting. Educational institutions developed what learning specialists call skill-based economics, curricula that taught students how gaming expertise could create economic value while simultaneously developing problem-solving capabilities, pattern recognition skills, and strategic thinking abilities that transferred to many professional contexts. Gaming became a legitimate subject for academic study and career development. The professional gaming industry experienced what sports economists call mainstream integration, as speedrunning competitions gained recognition as skilled performances worthy of the same respect accorded to traditional sports competitions. Corporate sponsors began supporting speedrunning events not just for entertainment marketing, but as demonstrations of human skill development and achievement. Media coverage of gaming communities shifted from what communications researchers call novelty framing, treating gaming as an interesting oddity, to expertise recognition that covered speedrunning achievements with the same seriousness applied to other skilled endeavors. Gaming accomplishments began appearing in mainstream news coverage alongside achievements in science, arts, and athletics. The psychological impact on gaming communities was profound as participants experienced what identity researchers call vocational validation, the recognition that activities they had pursued for intrinsic satisfaction were also valuable contributions to society. Many speedrunners reported increased confidence and social connection as their expertise gained broader recognition and respect. Local communities began hosting what event organizers call skill exhibitions, where community members could demonstrate gaming expertise, teach optimization techniques, and share the strategic thinking that characterized high-level play. These events became celebrations of human capability and learning rather than just entertainment, strengthening community connections around shared appreciation for skill development. The intergenerational effects were particularly notable as older adults began recognizing gaming expertise as a form of craftsmanship comparable to traditional skilled trades. Grandparents who had previously been skeptical of gaming began taking pride in grandchildren's speedrunning achievements, creating what family researchers call cross-generational skill appreciation that strengthened rather than divided family relationships. International cultural exchange around gaming expertise flourished as communities worldwide began sharing optimization techniques, strategic approaches, and skill development methods across linguistic and cultural boundaries. The universal appreciation for mastery and improvement created what global studies researchers call skill diplomacy that connected people through shared respect for human achievement. Professional development programs began incorporating what organizational psychologists call gaming-derived optimization training that taught business professionals the pattern recognition, rapid decision-making, and performance analysis skills that speedrunning communities had developed. The strategic thinking and attention to detail required for competitive gaming proved directly applicable to many professional contexts. Academic research into gaming expertise revealed what cognitive scientists call transferable mastery effects, evidence that the skills developed through speedrunning practice enhanced performance in other demanding cognitive tasks. This research provided scientific validation for what gaming communities had intuitively understood about the value of their expertise. The cultural shift was perhaps most visible in how language around gaming began to change. Instead of describing gaming as playing around or wasting time, communities began using terms like skill development, optimization practice, and strategic analysis that reflected the serious cognitive work involved in high-level gaming performance. Libraries and community centers began offering what educational programmers call digital literacy through gaming programs that used speedrunning and gaming optimization as entry points for teaching broader technical skills, strategic thinking, and collaborative learning approaches. Gaming became a pathway into rather than a distraction from serious educational engagement. The transformation in cultural attitudes created what social change researchers call positive identity feedback loops, as gaming communities gained confidence from social recognition, leading to increased innovation, skill development, and community building that further enhanced their contributions to society. The economic value of gaming expertise reinforced and accelerated its cultural acceptance. By the spring of 2027, gaming had achieved what cultural historians call full legitimacy, recognition as a valuable form of human skill development that deserved the same respect and support accorded to other areas of expertise and achievement. The cultural transformation was complete. Gaming was no longer seen as separate from serious pursuits, but as another domain where human creativity and dedication could flourish. It's essential to pause and reflect on the remarkable economic reorganization that had crystallized by the summer of 2027. What had begun as a cryptocurrency mining innovation had evolved into a fundamental restructuring of how digital labor was valued, distributed, and integrated with human creativity and skill development. The emergence of what economists now call the skill economy represented more than just a new way to generate digital currency. It embodied a completely different understanding of how economic value could be created through human expertise rather than resource consumption. The traditional industrial model that required massive capital investment in specialized equipment had been replaced by a distributed system where anyone could participate through skill development and creative achievement. Communities worldwide began experiencing what social economists describe as economic democratization, as access to cryptocurrency generation no longer required substantial capital investment, but could be earned through developing expertise in activities that people enjoyed pursuing. The barriers to economic participation dropped dramatically as skill-based mining required only standard gaming equipment that was becoming increasingly affordable due to the GPU redistribution. Educational institutions found themselves at the center of what learning economists call human capital development initiatives as gaming skills gained economic value alongside traditional academic subjects. Schools began offering programs that combined strategic thinking, optimization analysis, and skill development in ways that served both educational goals and economic preparedness. The environmental implications of the economic transformation were profound and positive. The shift from energy-intensive computational mining to skill-based validation had eliminated one of the largest sources of unnecessary electricity consumption in the technology sector, while creating economic opportunities that actually enhanced rather than depleted natural resources. International cooperation emerged around what global governance researchers call skill-based trade protocols that allowed communities worldwide to participate in the new economic system, regardless of their access to traditional industrial infrastructure or energy resources. Countries that had been excluded from traditional mining due to energy costs found themselves able to participate through their citizens' creative capabilities. The psychological effects on participants in the skill economy were remarkably positive as people experienced what work satisfaction researchers call intrinsic motivation alignment, economic activities that corresponded with personal interests and creative goals rather than contradicting them. Workers in the skill economy reported higher job satisfaction and lower stress than their counterparts in traditional employment. Local communities experienced what urban economists describe as creative economy activation, as skill-based mining created economic opportunities that kept talent and investment local rather than flowing to distant industrial centers. Gaming cafes, training centers, and skill development programs became sources of community economic activity and social connection. The technology industry adapted to serve what innovation researchers call human-centered value creation rather than computational optimization. Graphics card manufacturers began designing hardware optimized for skill development and creative applications rather than just mining efficiency, creating products that better served human creativity and learning. Financial institutions developed what banking researchers call skill-based lending programs that recognized gaming expertise and community reputation as forms of collateral for educational and business loans. The economic value of human skills became quantifiable in ways that traditional financial systems could recognize and support. The cultural implications extended far beyond gaming communities as society began recognizing that economic value could emerge from the pursuit of mastery and excellence in any domain. Artists, craftspeople, and other creative professionals found new models for monetizing their expertise without compromising their creative integrity or community connections. Research institutions began studying what they call post-industrial value creation patterns that emerged when economic systems rewarded human creativity and skill development rather than resource extraction or attention capture. The skill economy provided a real-world laboratory for exploring alternatives to traditional industrial economic models. The transformation had international implications as countries that invested in education, creativity, and skill development found themselves better positioned in the global skill economy than those that had focused primarily on resource extraction or manufacturing. Human development became recognized as essential economic infrastructure. Perhaps most significantly, the skill economy demonstrated what economists call positive sum value creation, economic activities that made everyone better off rather than redistributing fixed resources through competition. Skill development enhanced individual capabilities while contributing to community knowledge and cultural richness. The consolidation of these changes by 2027 had created what historians now recognize as a new phase of human economic development, characterized by the recognition that human creativity, skill, and community connection were not just byproducts of economic activity, but could be its primary sources of value creation. The stage was set for the comprehensive transformation that would characterize the late 2027 through 2030 period, as the principles proven by skill-based cryptocurrency mining began influencing every sector of the economy and every aspect of how societies understood the relationship between work, creativity, and human flourishing. The skill-based mining revolution began spreading across international boundaries with the same organic, community-driven growth that had characterized its initial emergence. Unlike previous technological disruptions that were often imposed through corporate expansion or government mandate, the transition to skill-based economics spread through what anthropologists call cultural resonance, the recognition that these systems aligned with deeply held values about human dignity, creativity, and community that transcended national and cultural boundaries. Japan's adoption of skill-based mining proved particularly fascinating to cultural researchers, as the country's gaming communities integrated traditional concepts of shokunin, artisanal mastery, with speedrunning expertise. Japanese speedrunners developed what they called digital craftsmanship, approaches that emphasized the patient pursuit of perfection over rapid achievement, creating distinctly Japanese variations of skill-based mining that reflected cultural values about dedication and incremental improvement. European communities brought their own cultural perspectives to skill-based economic systems, with Scandinavian countries developing what they called lagom gaming, balanced approaches to skill development that emphasized sustainability and community well-being alongside individual achievement. German communities integrated concepts of Bildung, holistic personal development, into gaming education programs that used skill-based mining as a foundation for broader learning about optimization, strategy, and collaborative problem-solving. The spread to developing economies proved particularly significant as skill-based mining provided economic opportunities that didn't require massive infrastructure investment or access to cheap energy. Rural communities in Global South countries found that their young people could participate in the global skill economy through internet connections and basic gaming equipment, creating what development economists call leapfrog economic participation that bypassed traditional industrial development stages. Indigenous communities worldwide found that skill-based mining aligned naturally with traditional values about the relationship between individual excellence and community benefit. Native American gaming communities integrated concepts of gift economy and community responsibility into their participation in skill-based networks, developing protocols that ensured individual achievements contributed to collective well-being and cultural preservation. The linguistic diversity of international speedrunning communities created fascinating cultural exchanges as optimization techniques and strategic knowledge crossed language barriers through gameplay demonstrations and collaborative experimentation. Gaming became what communication researchers call a universal language for sharing complex technical knowledge and strategic thinking across cultural and linguistic boundaries. African communities brought Ubuntu philosophy, the understanding that individual well-being is inseparable from community flourishing, to their implementation of skill-based mining systems. South African gaming cooperatives developed protocols that distributed skill-based earnings according to community needs rather than just individual achievement, creating models for collective economic participation that influenced global best practices. Middle Eastern communities found that skill-based mining provided economic opportunities that respected cultural values about education, skill development, and family responsibility. Gaming became recognized as a form of serious study and practice that contributed to both individual development and family economic security, gaining acceptance from community leaders who had previously been skeptical of gaming culture. Latin American communities integrated concepts of convivencia, harmonious community living, into their skill-based mining networks, developing systems that emphasized mutual support and shared learning alongside individual achievement. Brazilian gaming communities pioneered collective speedrunning, approaches where community members collaborated on optimization research and strategy development. The educational implications of international adoption were profound as universities worldwide began recognizing gaming expertise as legitimate academic achievement. Exchange programs developed around sharing optimization techniques and strategic approaches across cultures, creating what educational researchers call global skill diplomacy that connected young people through shared interests in excellence and improvement. International gaming competitions evolved from entertainment events to what sports economists call skill showcases that demonstrated human achievement and cultural exchange through friendly competition. These events became celebrations of human capability and international cooperation rather than nationalistic displays, fostering what peace researchers call competitive collaboration that strengthened rather than strained international relationships. The economic development implications were particularly significant for regions that had been economically marginalized by traditional industrial systems. Skill-based mining created what development researchers call distributed economic opportunity that allowed communities to participate in global economic systems through their human capabilities rather than natural resource extraction or low-wage manufacturing. Cultural preservation efforts found unexpected support through skill-based mining as communities developed gaming content and optimization techniques that reflected local cultural knowledge and values. Traditional strategic thinking, pattern recognition, and community problem-solving approaches found new expression through gaming expertise, creating what cultural anthropologists call digital cultural innovation that preserved traditional knowledge while adapting it to contemporary contexts. The environmental justice implications of the international spread were significant as communities that had been affected by resource extraction or industrial pollution found economic alternatives that enhanced rather than degraded their natural environments. Skill-based mining provided what environmental economists call clean economic development that created opportunity without environmental costs. Regional variations in skill-based mining implementation reflected local gaming cultures and technological preferences, creating a rich ecosystem of different approaches that enhanced rather than homogenized global gaming culture. Korean communities developed high-precision timing techniques, while Finnish communities focused on strategic analysis, and Australian communities pioneered collaborative optimization methods. International cooperation around skill-based mining standards created what global governance researchers call soft coordination mechanisms that established shared protocols while respecting cultural differences and local preferences. These collaborations became models for international cooperation on other challenges that required balancing global standards with cultural diversity. By 2028, the international adoption of skill-based mining had created what economists call a global skill commons, shared knowledge and economic opportunities that connected communities worldwide through mutual interest in human development and creative achievement rather than competitive resource extraction or market domination. The year 2028 marked what educational historians now call the Great Curricular Transformation, as schools worldwide began integrating skill-based mining principles into their core educational approaches. The recognition that gaming expertise had economic value created unprecedented opportunities to align student interests with academic learning, resulting in what pedagogical researchers describe as the most successful educational innovation since the development of public schooling systems. Primary schools developed what early childhood educators call playful economics curricula that introduced young students to optimization thinking, strategic analysis, and collaborative problem-solving through age-appropriate gaming activities. Children learned mathematical concepts through speedrunning analysis, developed reading skills through gaming guides and community discussions, and practiced scientific thinking through systematic experimentation with game mechanics and optimization techniques. Secondary schools created what curriculum designers call integrated gaming studies programs that combine traditional academic subjects with skill-based mining participation. Students learn statistics through analyzing their speedrunning performance data, developed communication skills through creating educational gaming content, and studied economics through participating in skill-based mining networks while earning actual economic value for their learning achievements. Computer science education experienced what technology educators describe as practical alignment breakthrough, as programming and system design courses could now use skill-based mining networks as real-world applications for student learning. Instead of theoretical exercises, students developed actual tools and systems that served gaming communities while learning fundamental computer science concepts. Mathematics education found new relevance as students discovered that optimization problems, statistical analysis, and strategic calculation had direct applications to their gaming interests and economic opportunities. What had often been abstract mathematical concepts became practical tools for improving performance and understanding complex gaming systems. Language arts education evolved to include what literacy researchers call gaming communication studies that recognized the sophisticated reading, writing, and analytical skills required for participating in gaming communities. Students developed communication abilities through gaming guides, community interaction, and collaborative strategy development that required high levels of literacy and expression. History and social studies curricula began including what cultural educators call digital culture studies that examined gaming communities as examples of human social organization, economic innovation, and global cooperation. Students learned about collaboration, competition, cultural exchange, and economic systems through studying the communities they participated in. Science education found powerful applications as students used gaming optimization as entry points for understanding physics, chemistry, and biology concepts that appeared in game mechanics. The systematic experimentation and hypothesis testing that characterized gaming optimization provided what science educators call authentic scientific practice that engaged students in genuine research methods. Arts education integrated what creative learning specialists call digital aesthetic studies that recognized gaming as a medium for artistic expression and cultural creation. Students developed visual design, storytelling, and creative problem-solving skills through gaming content creation while participating in economically meaningful activities. Physical education expanded to include what movement researchers call digital embodiment studies that examined the physical skills, coordination, and mind-body integration required for high-level gaming performance. Gaming became recognized as a form of skilled movement practice that developed coordination, timing, and spatial awareness. Special education services found that skill-based mining provided what inclusive education specialists call neurodiversity economic opportunity, as different cognitive styles and capabilities found economic value through various forms of gaming expertise. Students with autism, ADHD, and other neurological differences often excelled in gaming optimization, finding economic and social success through their unique cognitive strengths. Higher education developed what university researchers call applied gaming studies programs that prepared students for careers in the emerging skill-based economy while conducting research into optimization, community organization, and human performance that served both academic and practical purposes. Graduate programs emerged in gaming optimization, community management, and skill-based economic systems. Adult education programs found new relevance as what lifelong learning specialists call economic reskilling. Initiatives helped adults transition into skill-based economic participation. Community colleges offered gaming optimization courses for professionals seeking to supplement their income or change careers, while providing valuable lifelong learning opportunities. International educational exchange programs developed around what global education researchers call skill diplomacy initiatives that connected students worldwide through shared gaming interests and collaborative optimization projects. These programs fostered international understanding and cooperation while serving educational and economic goals. Teacher education programs evolved to prepare educators for what professional development specialists call integrated learning facilitation, that combined gaming expertise with pedagogical knowledge. Teachers learned to use skill-based mining as a foundation for interdisciplinary learning that connected student interests with academic achievement. Educational assessment practices adapted to recognize what learning measurement researchers call authentic achievement through gaming performance alongside traditional academic metrics. Students could demonstrate learning through gaming achievements that required and developed the same cognitive capabilities that traditional assessments attempted to measure. The psychological impact on students was profound as they experienced what educational psychologists call intrinsic motivation activation, engagement with learning that arose from genuine interest and saw immediate practical application rather than external pressure or distant goals. Student engagement, retention, and achievement improved dramatically across all academic subjects. Educational equity improved significantly as skill-based mining provided what access researchers call universal economic participation opportunities that didn't require expensive equipment or specific socioeconomic backgrounds. Students from all economic circumstances could participate in economically meaningful learning while developing valuable skills and knowledge. By 2029, the integration of skill-based mining with education had created what learning theorists call seamless learning ecosystems, where educational achievement, personal interest, economic participation, and community contribution were unified rather than competing goals. Education became a process of developing human capabilities that served both individual fulfillment and collective flourishing. As 2029 unfolded, the principles that had revolutionized cryptocurrency mining through gaming expertise began inspiring similar transformations across creative industries. What started as skill-based mining in speedrunning communities became the foundation for what cultural economists now call the creative validation revolution, a systematic recognition that artistic skill, craft mastery, and cultural creation deserved the same economic support that had been extended to gaming expertise. Digital artists found themselves at the forefront of this expansion as developers created what they called aesthetic proof protocols that could verify genuine human creativity and artistic skill through blockchain systems. Unlike the speculative and often environmentally harmful NFT markets that had characterized earlier digital art monetization, these new systems rewarded actual artistic development and community engagement rather than artificial scarcity or commercial hype. Traditional craftspeople discovered that their expertise in woodworking, pottery, textile arts, and metalworking could be verified and economically supported through what artisan communities called mastery documentation systems. These platforms allowed craftspeople to demonstrate their skill development, share knowledge with learning communities, and receive economic recognition for their contributions to cultural knowledge and artistic heritage. Musicians found that the precision, timing, and creative expression required for musical performance could be verified and rewarded through what audio engineers developed as sonic authenticity protocols. Instead of having their economic success dependent on traditional record label systems or streaming platform algorithms, musicians could receive direct economic support for their skill development and community engagement. The maker movement experienced what technology educators call invention validation, as engineering communities developed systems that could verify and reward genuine innovation, problem-solving, and technical creativity. Makers working on everything from electronics to mechanical devices found economic support for their experimental work and knowledge sharing rather than just their commercial products. Writing communities developed what literary scholars call narrative skill verification systems that could identify and reward genuine storytelling ability, character development, and linguistic creativity. Writers found economic support for their craft development and community engagement rather than depending solely on traditional publishing systems that often prioritized commercial appeal over artistic merit. Cooking and culinary communities created what food scientists call gastronomic mastery protocols that recognized the skill, creativity, and cultural knowledge involved in culinary arts. Chefs and home cooks could receive economic recognition for developing recipes, teaching culinary techniques, and preserving cultural food traditions. Photography communities established what visual arts researchers call compositional authenticity systems that could verify genuine photographic skill, artistic vision, and technical mastery. Photographers found economic support for their artistic development and educational contributions rather than depending solely on commercial photography markets. Dance and movement communities developed what kinesthetic researchers call embodied expression validation that recognized the skill, creativity, and cultural significance of movement arts. Dancers could receive economic support for their artistic practice, teaching contributions, and cultural preservation work. The expansion to creative fields created what cultural economists call universal skill recognition systems that acknowledged that human expertise and creativity in any domain deserved economic support if it contributed to cultural knowledge, community well-being, or artistic heritage. The arbitrary distinction between economically valuable and personally fulfilling activities began to dissolve. Educational institutions adapted to support what arts educators call integrated creative economics programs that prepared students for creative careers while they developed economically recognized skills. Art schools, music conservatories, and craft programs found their graduates better positioned for economic success while maintaining artistic integrity. International cultural exchange flourished as what global arts researchers call creative skill diplomacy, connected artists worldwide through shared interests in mastery, innovation, and cultural expression. Artists could learn from and collaborate with practitioners from different cultural traditions while receiving economic support for their cross-cultural learning and contribution. Local communities experienced what urban planners call creative economy activation, as skill-based economic systems created demand for artistic instruction, cultural events, and creative collaboration spaces. Communities invested in art centers, maker spaces, and cultural facilities that supported both artistic development and economic opportunity. The psychological impact on creative professionals was profound as they experienced what work satisfaction researchers call intrinsic value alignment, economic recognition that corresponded with artistic values and creative goals rather than contradicting them. Artists reported higher satisfaction and better mental health when their economic security supported rather than compromised their creative practice. Traditional arts institutions adapted to what cultural policy researchers call community-centered arts support, models that recognized skill-based economic systems as legitimate and valuable forms of arts funding. Museums, galleries, and cultural organizations began supporting skill-based creative programs alongside traditional grant and donation funding. The intergenerational effects were significant as older master craftspeople and artists found their knowledge and expertise economically valued in ways that supported both their financial security and the preservation of cultural traditions. Younger artists could learn from master practitioners while developing economically sustainable creative careers. Rural and economically marginalized communities found that creative skill-based economic systems provided what development researchers call cultural economic development opportunities that built on existing cultural assets rather than requiring external industrial investment. Traditional crafts, music, and artistic practices became sources of economic opportunity alongside cultural preservation. By late 2029, the creative economy expansion had demonstrated what cultural theorists call universal creative value, the recognition that human creativity and skill development in any domain could contribute to both individual flourishing and collective cultural wealth. The artificial separation between economic and artistic value had been replaced by systems that recognized creativity as fundamental economic infrastructure. The environmental implications of the skill-based economic transformation became dramatically apparent throughout 2029 and 2030 as researchers documented what environmental scientists now call the Great Energy Liberation. The massive reduction in unnecessary energy consumption that resulted from transitioning economic value creation from computational intensity to human skill development. The abandoned cryptocurrency mining facilities that dotted landscapes worldwide became symbols of what environmental historians call industrial recovery, as these energy-intensive operations were converted to community uses or returned to natural states. The electricity that had powered millions of mining rigs was redirected to support renewable energy development, electric transportation infrastructure, and community services that enhanced rather than degraded environmental quality. Climate change mitigation efforts received what environmental economists call the efficiency dividend, as the energy previously consumed by computational mining became available for productive uses like carbon capture technology, renewable energy storage systems, and electric vehicle charging networks. The skill-based economic transition released enough electrical capacity to power entire cities' transition to renewable energy systems. Local ecosystems experienced what conservation biologists document as industrial healing, as mining operations that had required extensive cooling systems, generated noise pollution, and consumed vast amounts of electricity were replaced by human-scale activities that enhanced rather than degraded environmental conditions. Former mining sites became community gardens, renewable energy installations, and environmental education centers. The psychological connection between economic activity and environmental stewardship strengthened as what environmental psychologists call aligned values integration became possible for participants in skill-based economies. Instead of feeling conflicted about economic activities that harmed the environment, people could pursue economic goals that actually supported environmental and community well-being. Agricultural communities found that skill-based economic systems provided what rural development researchers call sustainable economic diversification that complemented rather than competed with farming and environmental stewardship activities. Gaming expertise and creative skills could be developed alongside agricultural work, providing economic resilience that didn't require environmental degradation. Urban planning evolved to support what city designers call post-industrial community infrastructure that optimized for human creativity and skill development rather than industrial production or resource extraction. Cities began designing community spaces, educational facilities, and cultural centers that supported skill-based economic activities while enhancing environmental quality. International environmental cooperation strengthened as what global environmental researchers call shared sustainability benefits. From skill-based economic systems created incentives for countries to work together on climate change mitigation, rather than competing for resource extraction or industrial production that degraded environmental quality. Air quality improvements were measurable and significant as the reduction in industrial mining operations eliminated what atmospheric scientists call computational air pollution from the massive cooling systems and power consumption that had characterized energy-intensive cryptocurrency operations. Communities that had hosted mining facilities reported improved air quality and reduced respiratory health issues. Water system recovery occurred as former mining operations that had required extensive cooling water were converted to uses that enhanced rather than consumed water resources. Some former mining facilities became environmental research stations that studied water conservation and ecosystem restoration rather than consuming resources for artificial computational work. Renewable energy development accelerated as what energy systems researchers call liberated grid capacity became available to support solar, wind, and other sustainable energy systems rather than energy-intensive computational mining. The transition to skill-based economics made renewable energy transition more economically feasible and environmentally effective. Wildlife conservation benefited as what ecology researchers document as industrial noise reduction occurred when mining facilities stopped operating their cooling systems and mining rigs continuously. Wildlife populations near former mining sites showed improved reproduction and reduced stress indicators as industrial noise pollution was eliminated. The circular economy concept found practical application as what sustainability researchers call human-centered resource optimization became possible when economic value creation required minimal physical resources and energy consumption. Skill-based economic activities demonstrated how prosperity could increase while resource consumption decreased. Environmental education gained new relevance as what ecological literacy researchers call integrated environmental economics. Curricula could demonstrate how economic activity could actually support rather than degrade environmental quality. Students could see practical examples of economic systems that enhanced rather than harmed ecological well-being. Community resilience strengthened as what environmental justice researchers document as locally rooted economics provided economic security that didn't depend on resource extraction or environmentally harmful industries. Communities could maintain economic stability while enhancing rather than degrading their local environment. Carbon footprint calculations revealed what climate researchers call negative emission economics, as skill-based economic activities actually created net environmental benefits through supporting renewable energy development, reducing industrial energy consumption, and enabling lifestyle changes that decreased rather than increased environmental impact. The transformation demonstrated what environmental philosophers call post-scarcity ecology, economic systems that created abundance through enhancing rather than consuming natural and human resources. Environmental protection and economic prosperity were revealed to be complementary rather than competing goals when economic systems were designed around human creativity rather than resource extraction. By 2030, the environmental benefits of skill-based economics had created what sustainability researchers call regenerative economic models that actively improved environmental conditions while providing economic opportunity and community well-being. The false choice between environmental protection and economic prosperity had been replaced by integrated systems that enhanced both simultaneously. As we moved through 2030 and into 2031, social scientists began documenting one of the most unexpected and profound impacts of the skill-based economic transformation: the strengthening of human community bonds and social connections that had been frayed by previous decades of digital fragmentation and competitive individualism. What researchers now call the Great Social Reconnection demonstrated how economic systems based on skill development and community participation could heal social divisions that had seemed intractable. Intergenerational relationships experienced what family sociologists describe as wisdom bridge building, as older adults discovered that their life experience in patience, persistence, and skill development was directly relevant to success in skill-based economies. Grandparents who had once felt disconnected from their grandchildren's digital activities became mentors in the strategic thinking and disciplined practice that gaming expertise required. Local communities found that skill-based economic activities created what urban researchers call organic gathering spaces, as gaming centers, maker spaces, and skill development facilities became natural places where community members of all ages and backgrounds could interact around shared interests in learning and improvement rather than demographic similarities or economic status. The competitive dynamics of gaming transformed into what sports psychologists call constructive competition, where participants pushed each other toward excellence while maintaining supportive community relationships. Unlike zero-sum economic competition that created winners and losers, skill-based economic systems allowed everyone to benefit from each other's improvement and achievement. Social isolation, which had become a significant public health concern during the social media fragmentation era, began reversing as what community health researchers document as purpose-driven social connection emerged through skill-based economic participation. People connected with others around shared goals of skill development and community contribution rather than passive consumption of digital content. Mental health indicators improved significantly as what psychological researchers call agency and community integration characterized people's experience in skill-based economic systems. Participants reported feeling both individually empowered through their skill development and socially connected through their community contributions, addressing two major sources of contemporary psychological distress. Educational communities experienced what learning researchers describe as collaborative excellence culture, where students supported each other's achievement because individual improvement contributed to collective knowledge and community success. The artificial competition between students for scarce opportunities was replaced by collaborative skill development that benefited everyone. Workplace relationships improved as what organizational psychologists document as skill-based collaboration became more common when people could contribute their gaming and creative expertise alongside traditional professional skills. Teams became more inclusive and innovative as diverse forms of human expertise were recognized and valued. International relationships strengthened through what peace researchers call cultural skill exchange, as gaming communities and creative networks connected people across national and cultural boundaries around shared interests in mastery and improvement rather than political or economic competition. These connections created what diplomacy researchers call citizen diplomacy networks that fostered international understanding and cooperation. Economic inequality began decreasing as what economic researchers document as distributed skill opportunity provided economic participation pathways that didn't require inherited wealth or institutional access. People could develop economically valuable skills through dedication and practice regardless of their starting economic circumstances, creating more equitable opportunity distribution. Rural-urban divides diminished as what regional development researchers call location-independent skill economics, allowed people in rural areas to participate in global economic networks while maintaining their connection to local communities and landscapes. Geographic location became less determinative of economic opportunity as skill-based work could be performed anywhere with internet connections. Youth engagement with civic activities increased as what political participation researchers document as economic civic integration occurred when young people's gaming and creative expertise became economically valuable and socially recognized. Young people felt more connected to their communities and more optimistic about their economic futures, leading to increased civic participation and community contribution. Senior isolation decreased as what gerontology researchers call continued contribution opportunity became available through skill-based economic systems that valued the patience, persistence, and strategic thinking that older adults had developed through life experience. Seniors could contribute to and benefit from economic activities that matched their capabilities and interests. Cross-cultural understanding improved as what anthropological researchers document as skill-based cultural exchange occurred when people from different backgrounds connected through shared gaming and creative interests that transcended cultural and linguistic differences while celebrating cultural diversity in approaches to skill development and community organization. Social media use patterns shifted toward what communications researchers call purpose-driven digital connection, as people used digital platforms to coordinate skill development, share knowledge, and support community goals rather than for passive entertainment or social comparison. Digital tools began serving social connection rather than replacing it. Community resilience strengthened as what disaster preparedness researchers document as skill-based mutual aid networks developed through gaming and creative communities that could be activated to support community members during difficulties. The social connections formed around skill development provided practical support networks during emergencies and challenges. The transformation demonstrated what social theorists call post-individualistic prosperity, economic systems that created individual opportunity and achievement through community participation and mutual support rather than competitive isolation. Individual success and community well-being became mutually reinforcing rather than conflicting goals. By 2031, the social healing enabled by skill-based economic systems had created what sociologists call integrated community prosperity, where individual skill development, economic opportunity, environmental stewardship, and community well-being all supported and enhanced each other through aligned rather than competing incentives. The period from 2031 to 2032 witnessed what international relations scholars now call the Great Collaboration, as countries worldwide recognized that skill-based economic systems created opportunities for cooperative rather than competitive international relationships. The transformation from resource-based to skill-based economics fundamentally altered how nations related to each other, creating what diplomatic researchers describe as positive-sum global economics, where countries could enhance their prosperity by supporting rather than undermining other nations' skill development and cultural creativity. The United Nations established what they called the Global Skill Development Initiative that facilitated international exchange of optimization techniques, teaching methods, and community organization strategies that had proven successful in different cultural contexts. Instead of protecting competitive advantages, countries began sharing best practices that enhanced everyone's skill-based economic participation while preserving cultural diversity in approaches and applications. International trade patterns shifted toward what economists call expertise exchange, as countries began importing and exporting knowledge, techniques, and collaborative relationships rather than just physical goods or resource extraction rights. The most economically successful nations became those that could contribute to and benefit from global knowledge networks rather than those that controlled physical resources or manufacturing capacity. Cultural diplomacy experienced what international studies researchers describe as skill-based soft power, as countries gained international influence through their contributions to global skill development and creative innovation rather than through military or economic coercion. Nations that supported gaming expertise, artistic innovation, or technical creativity gained international respect and collaborative partnerships. Development assistance evolved toward what international development researchers call capacity-building collaboration, where wealthy countries supported skill development infrastructure in developing regions rather than just providing financial aid or technical equipment. International development became focused on enhancing human capabilities rather than creating economic dependency relationships. International scientific collaboration flourished as what research cooperation specialists document as global knowledge commons emerged when skill-based economic systems removed competitive pressures that had previously limited information sharing. Scientists could collaborate on global challenges while receiving economic support for their expertise and community contributions. Environmental cooperation strengthened as what climate diplomacy researchers call shared sustainability benefits became possible when countries' economic success wasn't dependent on resource extraction or industrial production that created environmental conflicts. Skill-based economies made environmental protection economically beneficial rather than costly for all participating countries. International education exchange expanded as what global education researchers document as universal skill diplomacy. Programs connected students worldwide through collaborative skill development projects that enhanced both individual capability and international understanding. Educational exchange became focused on mutual skill development rather than one-directional knowledge transfer. Conflict resolution improved as what peace studies researchers call collaborative problem-solving became more feasible when countries could address challenges through shared expertise rather than competitive resource allocation. International disputes increasingly focused on optimizing cooperative solutions rather than determining winners and losers in zero-sum competitions. International economic institutions adapted to support what global finance researchers call skill-based development finance that provided funding for education, community development, and cultural preservation rather than just industrial infrastructure or resource extraction projects. International banking began supporting human development as fundamental economic infrastructure. Migration patterns shifted as what demographic researchers document as skill-based mobility became possible when people could maintain economic connections to global skill networks regardless of their physical location. International migration became less driven by economic desperation and more characterized by cultural exchange and collaborative skill development. Global governance evolved toward what international law scholars call cooperative regulatory frameworks that established standards for skill verification, community protection, and knowledge sharing, while respecting cultural differences and national sovereignty. International law began protecting and facilitating human skill development as a universal right and global resource. International security cooperation strengthened as what defense studies researchers document as collaborative security became possible when countries' prosperity depended on global skill development and cultural creativity rather than competitive resource control. National security became focused on protecting and enhancing global human capability rather than just defending territorial or economic interests. Cultural preservation efforts gained international support as what heritage conservation researchers call living heritage economics, provided economic incentives for maintaining traditional skills, arts, and knowledge systems that contributed to global cultural diversity and skill development. International cooperation began protecting cultural knowledge as valuable global resources. Technology development became characteristically collaborative as what innovation researchers document as open innovation networks emerged when skill-based economic systems removed competitive pressures that had limited knowledge sharing. International collaboration on technology development accelerated when innovations could benefit everyone rather than creating competitive advantages for specific countries. International sports and cultural competition evolved toward what comparative culture researchers call collaborative excellence celebration, where international events focused on sharing techniques and celebrating human achievement rather than just determining national rankings. International competition became a venue for cultural exchange and mutual learning rather than just nationalistic display. The transformation demonstrated what global studies theorists call post-national prosperity, where countries could enhance their citizens' well-being through contributing to rather than competing with global human development. National success became measured by contributions to global skill development and cultural creativity rather than just domestic economic indicators. By 2032, international cooperation around skill-based economics had created what diplomatic historians call the Global Skill Alliance, an informal but powerful network of mutual support that connected countries through shared commitment to human development and cultural creativity rather than competitive economic or military relationships. As we moved through 2032 and into 2033, the technology industry underwent what innovation researchers now call the human-centered revolution. As engineers and designers began developing tools specifically optimized for supporting human skill development rather than replacing human capabilities or capturing human attention. The transformation represented a fundamental reorientation of technological innovation from automation and efficiency toward enhancement and empowerment of human creativity and expertise. Graphics processing technology experienced what hardware engineers describe as optimization reorientation, as GPU manufacturers began designing cards specifically for skill development rather than just computational power or mining efficiency. New graphics cards included features like precision timing analysis, performance pattern recognition, and collaborative learning support that helped gamers develop and demonstrate their expertise more effectively. Game development studios evolved toward what interactive design researchers call skill-based game design that created gaming experiences specifically intended to develop transferable cognitive capabilities, strategic thinking, and collaborative problem-solving skills. Games became personalized training systems that adapted to individual learning styles while maintaining the entertainment value that made skill development enjoyable. Artificial intelligence development shifted toward what human-AI interaction specialists call capability amplification systems designed to enhance rather than replace human expertise. AI tools became collaborative partners that helped skilled practitioners analyze their performance, identify improvement opportunities, and share knowledge with learning communities rather than competing with or substituting for human skills. Educational technology experienced what learning systems researchers document as integrated skill platforms that combined gaming expertise, creative development, and academic learning in unified systems that served both educational goals and economic preparation. Students could develop valuable skills while achieving traditional academic objectives through technology designed for human flourishing rather than institutional efficiency. Internet infrastructure evolved to support what network design researchers call community-centered connectivity that prioritized collaborative skill development, cultural exchange, and mutual support rather than content consumption or attention capture. Network architectures began optimizing for the kinds of sustained, meaningful interaction that characterized skill-based communities. Software development practices shifted toward what programming methodology researchers describe as human-supportive design that created tools specifically intended to enhance human capabilities rather than abstract them away through automation. Programming became focused on amplifying human creativity and expertise rather than replacing human involvement in complex tasks. Virtual and augmented reality technology developed what immersive experience researchers call skill amplification environments that allowed people to practice, learn, and demonstrate expertise in simulated contexts that enhanced rather than replaced real-world skill development. VR became a tool for accelerating human learning rather than escaping from human interaction. Blockchain and distributed systems technology evolved beyond cryptocurrency toward what decentralized computing researchers call community infrastructure systems that supported collaborative skill development, resource sharing, and knowledge preservation without requiring mining or energy-intensive validation. Distributed technology became a foundation for community empowerment rather than speculative investment. Manufacturing technology shifted toward what production innovation researchers document as skill-supportive tools that enhanced rather than replaced human craftsmanship and creativity. 3D printing, automation, and fabrication tools became assistants to human makers rather than substitutes for human involvement in creative production. Communication technology developed what social interaction researchers call meaningful connection platforms, designed specifically to support the kinds of sustained, thoughtful interaction that characterized skill-based communities rather than the fragmented, attention-capturing patterns that had characterized earlier social media systems. Scientific instrumentation evolved toward what research methodology specialists describe as citizen science integration, that allowed skilled community members to contribute to scientific research through their gaming expertise, pattern recognition capabilities, and collaborative analysis skills, rather than requiring specialized scientific training for meaningful participation. Medical technology development incorporated what healthcare innovation researchers call community health integration, that recognized gaming skills, creative expertise, and collaborative community participation as contributors to physical and mental health, rather than distractions from health and wellness goals. Accessibility technology advanced toward what inclusive design researchers document as universal skill access, that ensured people with diverse physical and cognitive capabilities could participate in skill-based economic systems through adaptive interfaces, alternative input methods, and collaborative accommodation systems that enhanced rather than limited human capability diversity. Environmental monitoring technology evolved to support what ecological systems researchers call community environmental stewardship, that allowed skill-based communities to contribute to environmental protection and restoration through their collaborative capabilities, creative problem-solving, and sustained attention to complex challenges. The transformation demonstrated what technology philosophy researchers call human-centric innovation, where technological development was guided by questions about how to enhance human creativity, community connection, and skill development, rather than how to increase efficiency, reduce costs, or capture market share through competitive advantage. International collaboration on technology development flourished as what innovation cooperation researchers document as global skill technology commons emerged when countries could benefit from sharing rather than hoarding technological innovations that enhanced human capability and community well-being. By 2033, the technological renaissance had created what systems design theorists call symbiotic human-technology integration, where technological tools enhanced human capabilities while human expertise guided technological development, creating positive feedback loops that accelerated both technological innovation and human skill development simultaneously. As we observe the world of 2033 and 2034, educational psychologists and child development researchers began documenting what they now call the skill-native generation. Children who had grown up entirely within skill-based economic systems and whose cognitive development, social relationships, and understanding of value creation were fundamentally different from previous generations. These young people represented what developmental researchers describe as the first generation to experience complete alignment between their natural learning inclinations and economic opportunity structures. Children entering primary school during this period demonstrated what early childhood researchers call integrated learning orientation, where the development of gaming skills, creative abilities, strategic thinking, and collaborative problem-solving was seamlessly connected to both academic achievement and economic preparation. These children experienced learning as a unified process rather than separating education from practical application or personal interest from economic value. The cognitive development patterns of skill-native children showed what neurodevelopmental researchers document as enhanced executive function, characterized by improved sustained attention, strategic planning, and collaborative coordination compared to previous generations. Growing up with skill-based economic systems had provided optimal conditions for developing the cognitive capabilities that these systems both required and reinforced. Social development among skill-native children reflected what child psychology researchers call collaborative excellence orientation, where children naturally understood that individual achievement and community well-being were mutually reinforcing rather than competing goals. These children developed leadership skills, conflict resolution capabilities, and cultural competencies through their participation in diverse skill-based communities. Educational achievement patterns showed what learning outcome researchers document as intrinsic motivation optimization, where children achieved higher academic performance while reporting greater satisfaction and lower stress about their educational experiences. The alignment between personal interests and educational goals had eliminated much of the motivational conflict that had characterized previous educational systems. Career preparation took on what vocational development researchers call organic professional development, characteristics as children could begin developing economically valuable expertise through activities they enjoyed and were naturally good at, rather than having to wait until adulthood to discover and develop their professional capabilities and interests. International cultural competency developed naturally as what global education researchers document as skill-based cultural integration, where children connected with peers worldwide through shared interests in skill development, while learning to appreciate and celebrate cultural differences in approaches, values, and community organization styles. Creative development flourished as what arts education researchers call economic creative validation, provided children with recognition and support for artistic skill development from an early age, eliminating the artificial separation between creative expression and economic preparation that had often forced young people to choose between artistic interests and financial security. Environmental awareness developed through what ecological education researchers document as lived sustainability integration, as children experienced economic systems that actually enhanced rather than degraded environmental quality, giving them practical experience of how human prosperity and environmental health could support each other. Technology relationships were characterized by what digital literacy researchers call tool mastery orientation, where children learn to use technology as instruments for achieving their goals rather than being captured or manipulated by technological systems designed to exploit their attention or influence their behavior. Community engagement patterns showed what civic development researchers document as natural civic integration. As children participated in community decision-making, resource sharing, and mutual support through their involvement in skill-based economic activities, developing civic capabilities and community commitment from an early age. Mental health indicators among skill-native children showed what child psychology researchers call developmental well-being optimization, with lower rates of anxiety, depression, and behavioral difficulties compared to previous generations, reflecting the psychological benefits of growing up in systems that supported rather than frustrated their natural development patterns. Physical development benefited from what pediatric health researchers document as active skill integration, as many forms of skill-based economic participation required sustained physical coordination, timing precision, and mind-body integration that supported rather than competed with physical health and development. Intergenerational relationships were characterized by what family development researchers call mutual skill respect, where children could contribute economically valuable expertise to family well-being while learning from adult experience and wisdom, creating more balanced and mutually supportive family dynamics than had been typical in previous economic systems. Academic research capabilities developed early as what educational research specialists document as natural scientific thinking, emerged when children regularly engaged in systematic experimentation, hypothesis testing, and collaborative analysis through their skill development activities, acquiring research methodologies through practical application rather than abstract instruction. The transformation had created what child development theorists call optimal development conditions, where children's natural learning inclinations, social development needs, creative interests, and economic preparation requirements were all supported by the same activities and community relationships rather than competing for time and attention. International adoption of child-centered skill development created what global child development researchers document as universal positive development, patterns where children worldwide could develop their unique capabilities while connecting with global communities and contributing to international cooperation and understanding. By 2034, the skill-native generation had demonstrated what human development researchers call actualized human potential, cognitive, social, creative, and economic development that approached what child development theory had always suggested was possible when children's natural capabilities were properly supported rather than constrained by artificial separations between learning, playing, working, and contributing to community well-being. As we approach our present moment in 2035, futurologists and systems theorists began examining what they call the infinite potential horizon, opened by the transition to skill-based economic systems. Rather than reaching a stable endpoint, the transformation had revealed what complexity researchers describe as evolutionary economic dynamics, where human creativity and skill development created ever-expanding possibilities for value creation, community enhancement, and individual flourishing. Research institutions began exploring what innovation studies specialists call next-generation skill integration, possibilities that could expand skill-based economic systems beyond gaming and traditional creative arts into areas like emotional intelligence, relationship building, cultural bridge making, and wisdom development that had never been recognized as economically valuable, despite their crucial importance to human well-being and social function. International development organizations investigated what they termed global skill commons expansion initiatives that could extend skill-based economic participation to communities that had been excluded from traditional economic systems, creating what development economists call universal economic inclusion, based on human capability development rather than capital investment or resource access. Environmental restoration projects began incorporating what ecological economics researchers describe as regenerative skill application, where human expertise in pattern recognition, strategic planning, and collaborative organization was applied to environmental healing and ecosystem restoration, creating economic value through activities that actively improved rather than consumed natural resources. Space exploration programs developed what aerospace collaboration researchers call deep space skill networks that could support human space exploration through Earth-based skill communities that provided strategic analysis, creative problem-solving, and collaborative decision-making support for space missions, creating economic participation in humanity's expansion beyond Earth. Healthcare systems explored what medical innovation researchers describe as community health skill integration that could apply gaming expertise, creative capabilities, and collaborative organization skills to health promotion, disease prevention, and community well-being initiatives that enhanced rather than just treated human health. Scientific research expanded toward what citizen science researchers call democratic scientific participation, where skill-based communities could contribute to research on climate change, medicine, astronomy, and other scientific challenges through their pattern recognition capabilities, strategic thinking skills, and collaborative analysis abilities. Educational evolution continued toward what learning systems researchers document as lifelong skill development integration, where formal education, professional development, personal growth, and economic participation became unified processes that continued throughout people's lives rather than being separated into distinct phases or competing priorities. International cooperation deepened through what global governance researchers call collaborative challenge resolution initiatives that applied skill-based community capabilities to international problems like climate change, poverty elimination, disease eradication, and conflict resolution that required sustained collaborative effort rather than just financial resources or technological solutions. Technological development accelerated toward what human technology integration researchers describe as symbiotic innovation, where human skill development and technological advancement enhanced each other through feedback loops that created both better technology and more capable humans, rather than technology replacing human involvement. Cultural preservation expanded through what heritage conservation researchers call living culture economics, that provided economic support for maintaining and developing traditional skills, knowledge systems, and cultural practices, while adapting them to contemporary contexts and global participation. Urban planning evolved toward what sustainable city researchers document as skill-based community design that optimized physical environments for human skill development, creative collaboration, and community well-being rather than just economic efficiency or resource consumption minimization. The philosophical implications continued expanding as what social philosophy researchers call post-scarcity consciousness developed among populations that had experienced economic systems based on human capability enhancement rather than resource competition, creating new understandings of human nature, social possibility, and the purpose of economic activity. Research into consciousness and human potential gained practical application as what consciousness studies researchers describe as applied human development became economically valuable, creating incentives for investigating and developing human capabilities that had never been systematically explored or supported. International cultural exchange accelerated through what global culture researchers call skill-based culture sharing that connected communities worldwide through collaborative learning and mutual capability enhancement, while preserving and celebrating cultural diversity in approaches, values, and knowledge systems. The expansion demonstrated what systems evolution theorists call open-ended human potential, where each advancement in skill-based economic systems revealed new possibilities for human development and community enhancement rather than reaching limits or creating saturation points. Intergenerational knowledge sharing flourished as what wisdom studies researchers document as living wisdom economics that provided economic recognition for the knowledge sharing, mentorship, and cultural guidance that elder community members could provide to younger generations, developing their skills and capabilities. By 2035, the continuing evolution of skill-based economic systems had created what futurists call infinite possibility economics, where human creativity, skill development, and community enhancement generated ever-expanding opportunities for individual fulfillment and collective flourishing without apparent limits or negative consequences. The transformation had revealed what human potential researchers describe as boundless creative capacity, evidence that human beings could continue developing new capabilities, enhancing existing skills, and creating additional value indefinitely when economic systems supported rather than constrained human development and community well-being. As we arrive at the peaceful conclusion of our exploration through this remarkable transformation, we find ourselves witnesses to what historians now recognize as humanity's most successful demonstration that economic prosperity, individual fulfillment, and community well-being can be not just compatible but mutually reinforcing when systems are designed around human flourishing rather than resource extraction or attention capture. The journey we have traced together, from the GPU scarcity crisis of the 2020s through the accidental discovery that speedrunning could replace energy-intensive mining to today's abundant, skill-based economy, reveals profound truths about human nature and human possibility. When faced with systems that seemed intractable and problems that appeared unsolvable through conventional approaches, human creativity found solutions that were not just effective but elegant, not just functional but joyful. What makes this transformation particularly remarkable is how it emerged, not through top-down planning or regulatory intervention, but through the organic recognition that human skill, creativity, and community connection were more valuable than the computational brute force that had characterized cryptocurrency mining. The solution appeared when someone noticed that the precision and dedication required for speedrunning contained exactly the kinds of proof of human engagement that could secure economic networks more efficiently than energy-intensive calculations. The technical innovations that enabled this transformation, skill verification protocols, human authenticity signatures, and community-based economic validation, proved that sophisticated economic systems could operate through human excellence rather than resource consumption. The false choice between economic efficiency and human values was revealed to be exactly that, a false choice based on limited imagination about what economic systems could accomplish. The economic transformation from scarcity to abundance, from energy waste to skill development, from competitive isolation to collaborative enhancement demonstrates that sustainable prosperity emerges naturally when economic incentives align with rather than oppose human psychological needs for mastery, purpose, and community connection. The social healing that accompanied this economic transformation reveals how much of the contemporary anxiety, isolation, and conflict had been aggravated by economic systems that required people to compete rather than collaborate, that rewarded extraction rather than creation, and that captured attention rather than developed capability. The environmental renaissance that followed the collapse of energy-intensive mining demonstrates how human prosperity and ecological health can mutually reinforce when economic value creation enhances rather than depletes natural and human resources. The great energy liberation freed massive amounts of electricity for productive uses, while creating more rather than fewer economic opportunities. The cultural elevation of gaming expertise, creative skills, and collaborative capability from dismissed hobbies to recognized economic assets reveals how much human potential had been overlooked by traditional economic systems that valued only narrow forms of productivity while ignoring the vast range of human capabilities that actually contribute to individual and community flourishing. The international cooperation that flourished as countries discovered their prosperity increased through supporting rather than competing with other nations. Skill development shows how economic systems based on human capability enhancement naturally create positive-sum rather than zero-sum dynamics that benefit everyone simultaneously. The educational revolution that occurred when learning aligned with economic preparation and personal interest demonstrates how artificial the separation between education and application had always been, and how much more effective learning becomes when it serves immediate purposes that students can understand and experience. The technological renaissance that emerged when innovation focused on enhancing rather than replacing human capabilities proves that technology can amplify human creativity rather than substitute for it, when development is guided by questions about human flourishing rather than just efficiency, cost reduction, or market capture. The children growing up in this transformed world, confident in their capabilities, connected to their communities, contributing economically through activities they enjoy, and experiencing technology as a tool rather than a master, represent what human development has always been capable of creating when systems support rather than frustrate natural learning and growth patterns. Perhaps most significantly, this transformation reveals that human beings possess remarkable wisdom about their own well-being and that of their communities. When provided with genuine choices rather than manipulative pressure, people consistently choose conditions that support creativity, collaboration, and mutual enhancement over extraction, competition, and individual accumulation at community expense. The gentle revolution is complete, having transformed not just how graphics cards are distributed or how cryptocurrency is generated, but how human beings understand the relationship between individual achievement and community well-being, between economic activity and environmental stewardship, between technological capability and human flourishing. In the quietly humming graphics cards that now serve creativity rather than computational waste, in the strengthened communities that coordinate mutual support through thoughtful technology, and in the peaceful prosperity that emerges when human skill and community connection become the foundation for economic value, we can rest in the recognition that humanity proved capable of creating systems worthy of our highest aspirations. The future that seemed impossible to observers in the 2020s, abundant hardware, environmental healing, meaningful work, strong communities, international cooperation, and technology that serves human flourishing, has become simply the present reality of 2035, achieved not through struggle or sacrifice, but through the recognition that human creativity and community connection are the most valuable resources any economy could ever hope to cultivate. As you drift toward peaceful sleep in this world where your skills matter, your creativity has value, your community connections provide both economic security and social fulfillment, you can rest knowing that when humanity faced its greatest technological and environmental challenges, it responded not with fear or force, but with ingenuity, collaboration, and an unwavering commitment to creating conditions where both individual excellence and collective well-being could flourish together. Sweet dreams, and may your rest be as satisfying as a perfect speedrun executed in service of both personal achievement and community benefit. If you've enjoyed this exploration of humanity's peaceful gaming revolution, I invite you to gently engage with our community. Like this video, if it brought you insight or nostalgia for both the gaming culture we know and the economic possibilities we might create. Share your thoughts in the comments about your own gaming experiences and how you've seen skills develop in unexpected ways. Subscribe to join our ongoing explorations of how technology, creativity, and community might intersect to serve human flourishing in surprising ways. Perhaps consider what skills you've developed through gaming or creative pursuits that might have value you haven't fully recognized. The transformation we explored together may seem fantastical, but it began with the simple recognition that human expertise has value worth protecting and supporting. What capabilities do you possess that deserve more recognition in the world we're building together? Sweet dreams, and may your rest be as satisfying as knowing that human creativity always finds a way to turn even the most serious challenges into opportunities for play, learning, and community connection.